The Great Church, brought to you by Digi-Key and Adafruit. Every single week, Lady Ada uses her powers of engineering to help you, yes you, find the things that you are looking for on, I think, the world's biggest supplier of electronics and more.
Yeah, easily.
Digi-Key.
Yeah.
Lady Ada, what you looking for?
Okay, so we just talked about doing a bunch of e-ink stuff, getting some e-ink displays up and running. I'm gonna, it's like, I could tell these people like e-ink is one of the few things where, even before using AI assistants, like it's just like mind numbing. It's like very frustrating to work with e-paper displays because there's very little documentation. They don't work. There's like, you kind of don't really know what you're doing. And eventually it does work, but it's like somehow you just lost like 5 hours. And so I'm kind of, this week I was like, well, like the weather's good and I have some extra childcare, so let's do e-ink stuff. And so I got a bunch of displays up and running. And I'd like to kind of expand to do more displays because I want to revisit the MagTag, but also want to make a bigger version using like maybe this like 4.2-inch e-ink display, like cool big display. So one thing that we do when we have breakout boards for e-paper displays is that if you have some e-ink like this is 400 by 300 pixels. So let's just bring this up. So this is 400 times 300 pixels times 2 colors per pixel, and then it's 8 bits per byte. So you need 30 kilobytes to buffer the display. And what's interesting about e-ink displays is unlike TFT displays, which almost always like the little, the little plug-in SPI displays. These plug-in displays 99% of the time have built-in video memory. You just tell it what window you want to write and you can draw within it. And so you don't have to buffer the full display. You just draw whatever pixels you want, which is great because otherwise you need like 500 kilobytes of video RAM. E-ink displays are different. E-ink displays do not have built-in memory. They write you write the RAM. The RAM is buffered to the outside of the display, and then you usually turn the display off, and so you lose that RAM. Like there's no like back RAM to reference. And so when you draw to these displays, you basically have to have the whole image ready to go, and then you lit the whole thing at once to display. And so in this case, for example, like we did the math, you need 30 kilobytes of RAM. Now, if you have like, an ESP32, an RP2030, or like, an IMX-RT, 30 kilobytes is nothing. You're like, no problem, malloc it, you got it, you do it. But sometimes first off, there's a lot of people who are still using older microcontrollers, like at Megas, or maybe like smaller PICs, or, other small chips, maybe even ESP8266s, which will kind of, you can do 16K, but once you get 64K, they start to be like, I really need that RAM for doing Wi-Fi stuff. And so what we do is we often, on the breakout boards, have some RAM on top, some SRAM, because e-ink displays are such slow to update. They take a really long time compared to TFTs, which are like nearly instantaneous, 60 frames, 30 frames a second. These are like easily a second, and the bigger displays, especially the color displays, you're talking about like 17, 20, 30 seconds to update the display. It doesn't really matter if you have your SRAM off chip where you keep your image buffer, because it's only going to add 200 milliseconds or whatever, maybe, to the display time. And it's worth it if you can, if the chip isn't expensive and you're using like an Arduino Uno, you don't want to update, this gives you access to drawing to those big displays. So let's look for SRAM chips, and we're going to look specifically for one that does SPI, because I2C is going to be a little too slow. Also, we already have SPI interface on the board because the e-ink display is SPI. So this is for active, and then there's non-volatile and volatile. So you're going to spend much more for non-volatile, which means it stays, it's like FRAM, it'll stay after you remove power, but we don't actually need that because we're just, we draw the buffer over every single time. Let's look only for surface mount chips so we can easily mount it. And then another thing we want to look for is the size. And so it's a little confusing because Let me see where the sizes are. Sorry. Clock frequency, memory organization. So there's memory size, and that's always done in kilobits. And then there's organization, which tells you, like, is it in 6? Sometimes it's 32 bits wide. We actually don't care. We're probably going to end up with 8 bits. But let's do the math on that, the memory size. Now, remember, I showed you one that was 400 by 300. But actually, if you're looking at the 7-color ASEP, like the very large, beautiful color displays, those are about 640 by 480-ish. So just the number of pixels is 300,000 pixels. And then you have 7-color, but those are packed, so it's 3 bits per. So each pixel has 3 bits, and then you divide by 8 to convert to bytes. So you basically need 128 kilobytes, but it's okay for it to be a little bit bigger. So let's only look at, and this is bits, and so it's 1 megabit almost. But let's look at, let's do by memory organization. It's a little easier to understand. So let's look at only times 8, because it's a little less confusing. We could do 64, but let's start with, let's just pick 64 just in case, there's some cases which we might want it. 128 by 8, 256K by 8, and 512K by 8. That's plenty. And let's apply. So now we're only going to look at the memory size, the sizes that make sense, because you're going to always pay more for bigger memory. And then we want SPI, so we'll get rid of the I²C. And then finally, there's some good options, but we want to, start to see there's a bunch of chips. We want to look for ones that can do the voltages we need. 2.2 volts is way too small. We're going to do 3.3 volt logic. So we just want to make sure that we select all the voltages that are within our range. Lastly, I don't want a BGA, so I'm just going to select all the ones that are not BGA, just get rid of the few that aren't. And there's NV SRAM, but again, I think that's going to be more expensive. We're just going to filter by cost. So let's put in, price at 250, and then we will sort by 250. And we got some good options. So the 23 series, this is a generic name. There's the 24 series for EEPROM, 25 series for SPI flash. 23 series is SPI SRAM. And you see these are 64K. We want, maybe we want a little bit bigger. So you're going to pay more. The cheaper ones are always going to be the 64. So let's start looking at 128. So this is 1 megabit, 128K. And looks like there's a couple options. This one is, the least expensive, but there's, a few. ISI has some, Microchip has some. Some of these are more or less expensive. I guess maybe depending on the volt. Some of them do only 3.6 volts. Some of them go up to 5. Again, I have level shifting on these boards, and I'm dealing with 3 volt logic. So I think I'm just going to go with this one. This one's fine. So it's 1 megabit SPI. You can do quad SPI if you want, but normal SPI is fine. And 1 megabit, this is plenty large, 128K. And then if I don't need that much memory, you save $1 by going to this one, 64 kilobytes, 512 kilobits. Same pinout. The good news, all of these are very code compatible. It's just how much memory you get to address. So one thing that's nice is on the breakout boards for our smaller displays, I use a 16K or 32K kilobyte RAM. And as I'm going to get to the bigger displays, I'll put a bigger RAM on to match that, the display resolution. So this is my pick for external SRAM. Could be very useful for you because, again, sometimes you can't add more RAM and you don't mind if it's slow. You don't have PSRAM support. SRAM is inexpensive and easily available.
It's a great search. Useful for you and useful for you. You can use the inflection different. It's a great search.
Where in the world